This episode is brought to you by Cisco Educational Premium. Did you know that the general theory of relativity is also known as Einstein field equations? These equations relate the geometry of space-time to distribution of matter within it. These equations are analogous to Maxwell's equations of electromagnetism. Only here we are dealing with space-time geometry. Einstein's field equations are partial differential equations. They can be written in the form G sub uv plus G, a Hill simple thing, G uv is equivalent to K T sub mu v, where G mu v is Einstein tensor, G mu v is a metric tensor, T mu v is a stress energy tensor, and that Hill symbol is the cosmological constant, and K is the Einstein gravitational constant. Einstein field equations can be defined as G mu v is equivalent to R mu v minus half R G mu v. The term R mu v is the Ricci curvature tensor, and R is the scalar curvature. It is a second degree tensor depending only on the metric tensor and its first and second derivatives. Einstein gravitational constant can be expressed as a function of gravity. In this form, K will be equivalent to 8 pi G on C raised to 4, which is roughly equivalent to 2.077 times 10 raised to negative 43 n raised to negative 1, where we have a G to be the Newtonian constant of gravitation, and C is the speed of light in a vacuum. Einstein field equations can be expressed as a function of time. Here it is expressed as R mu v minus half R G mu v plus lambda G mu v is equivalent to KT mu v. The expression on the left represents curvature of spacetime, and each term here has units of length squared. Length 1 has units of 1 on length square. The right side represents the stress energy momentum content of spacetime. Einstein field equations work well with geodesic equation. These equations together are able to tell us how freely falling matter moves through spacetime. Matter curves spacetime, and spacetime tells matter how to move. Cosmological constant was initially absent in Einstein field equations. Einstein later added it to his original version of EFT to allow for a universe that is static. This was, however, unsuccessful as evidenced by astronomical observations. Yet the equations still work well with it. This shows that at times in life we need mistakes and imperfections to be perfect. Solutions of Einstein field equations are metrics of spacetime. These metrics describe the structure of spacetime surrounding the inertial motion of objects in the spacetime. This is successful, although the equations cannot always be completely solved since they are nonlinear. We can have exact solutions for Einstein field equations. These cases are quite surprising, and study on these exact solutions to find out what they mean is one of the current activities of cosmology. This study has even led to prediction of black holes and to different models of evolution of the universe. Einstein field equations were first published in 1915. These equations were published by Albert Einstein himself in his 1915 paper. Einstein came up with them by first obtaining field equations in a vacuum in a rather geometric fashion. After this, you obtain field equations in the presence of matter from the field equations in a vacuum. This episode is brought to you by Cisco Educational Premium. We do know that continuity equation or transport equation is consistent with Schrodinger equation. A continuity equation or transport equation is an equation that describes the transport of some quantity. It is particularly simple and powerful when applied to a conserved quantity, but can be generalized to apply to an extensive quantity. Since mass, energy, momentum, electric charge, and other natural quantities are conserved under their respective appropriate conditions, a variety of physical phenomena may be described using continuity equations. Continuity equations are a strong and local form of conservation laws. For example, a weak version of the law of conservation of energy states that energy can neither be created nor destroyed. That is, the total amount of energy in the universe is fixed. This statement does not rule out the possibility that a quantity of energy could disappear from one point while simultaneously appearing at another point. A stronger statement is that the energy is locally conserved. Energy can neither be created nor destroyed, nor can it teleport from one place to another. It can only move by a continuous flow. A continuity equation is the mathematical way to express this kind of statement. For example, the continuity equation for electric charge states that the amount of electric charge in volume of space can only change by the amount of electric current flowing into or out of that volume through its boundaries. Continuity equation more generally can include sink or source terms, which allow them to describe quantities that are often but not always conserved, such as the density of molecular species, which can be created or destroyed by chemical reactions. In an everyday example, there is a continuity equation for the number of people alive. It has a source term to account for people being born and a sink term to account for people dying. Any continuity equation can be expressed in an integral form in terms of a flux integral, which applies to any finite region, or in a differential form in terms of the divergent operator, which applies at that point. Continuity equations underlie more specific transport equations such as the convection diffusion equation, Boltzmann transport equation, and Navier-Stokes equations. Flows governed by continuity equations can be visualized using a Sankey diagram. A continuity equation is useful when a flux can be defined. To define flux, first there must be a quantity Q which can flow or move, such as mass, energy, electric charge, momentum, number of molecules, etc. Let ρ be the volume density of this quantity, that is the amount Q per unit volume. The way that this quantity Q is flowing is described by its flux. The flux of Q is a vector field, which we can denote as J. Here are some examples and properties of flux. The dimension of flux is the amount Q flowing per unit time through a unit area. For example, in the mass continuity equation for flowing water, if 1 gram per second of water is flowing through a pipe with cross-sectional area 1 centimeter square, then the average mass flux J inside the pipe is 1 gram per second per square centimeter, and its direction is along the pipe in the direction that the water is flowing. Outside the pipe, there is no water. The flux is zero. There is a velocity field U which describes the relevant flow. In other words, if all quantity Q at a point x is moving with velocity ux, then the flux is by definition equal to the density times the velocity field. J is equivalent to rho u. For example, if in the mass continuity equation for flowing water, u is the water's velocity at each point and rho is the water's density at each point, then J will be the mass flux. In a well-known example, the flux of electric charge is the electric current density. If there is an imaginary surface S, then the surface integral of flux over S is equal to the amount Q that is passing through the surface S per unit time. Note that the concept that is here called flux is alternatively termed flux density. The integral form of the continuity equation states that the amount Q in a region increases when additional Q flows inwards through the surface of the region and decreases when it flows outward. The amount Q in a region increases when Q is created inside the region and decreases when Q is destroyed. Apart from these two processes, there is no other way for the amount of Q in a region to change. Mathematically, the integral form of the continuity equation expressing the rate of increase of Q within a volume is as shown, where S is any imaginary closed surface that encloses a volume V. Double integral ds on S denotes a surface integral over that closed surface. Q is the total amount of the quantity in the volume V. J is the flux of Q. T is time. Sigma is the net rate that Q is being generated inside the volume V per unit time. When Q is being generated, it is called a source of Q and makes sigma more positive. When Q is being destroyed, it is called a sink of Q and makes sigma more negative. This term is sometimes written as shown, or the total change of Q from its generation or destruction inside the control volume. In a simple example, V could be a building and Q could be the number of people in the building. The surface S would consist of the walls, doors, roof, and foundation of the building. Then the continuity equation states that the number of people in the building increases when people enter the building. An inward flux through the surface decreases when people exit the building. An outward flux through the surface increases when someone in the building gives birth, a source, sigma greater than 0, and decreases when someone in the building dies, a sink, sigma less than 0. By the divergence theorem, a general continuity equation can also be written in a differential form as shown, where del dot is divergence, rho is the amount of the quantity Q per unit volume, J is the flux of Q, T is time, sigma is the generation of Q per unit volume per unit time. Terms that generate Q, for instance, sigma greater than 0, or remove Q, for instance, sigma less than 0, are referred to as sources and sinks respectively. This general equation may be used to derive any continuity equation ranging from as simple as the volume continuity equation to as complicated as the Navier-Stokes equation. This equation also generalizes the advection equation. Other equations in physics, such as the Gauss law of the electric field and Gauss law for gravity, have a similar mathematical form to the continuity equation, but are not usually referred to by the term continuity equation, because J in those cases do not represent the flow of a real physical quantity. In the case that Q is a conserved quantity that cannot be created or destroyed, such as energy, sigma is equivalent to 0, and the equations become partial rho on partial t plus del dot j is equivalent to 0, as shown. In electromagnetic theory, the continuity equation is an empirical law expressing local charge conservation. Mathematically, it is an automatic consequence of Maxwell's equations. Although charge conservation is more fundamental than Maxwell's equations, it states that the divergence of the current density J in amperes by square meter is equal to the negative rate of change of charge density rho in coulombs per cubic meter. Del dot J is equivalent to negative partial rho on partial t. One of the Maxwell equations, Ampere's law with Maxwell's correction, state as shown. Taking the divergence of both sides, the divergence and the partial derivative in time commute results as shown. But divergence of a curl is 0. So we have also but Gauss law, another Maxwell equation, states del dot d is equivalent to rho, which can be substituted in the previous equation to yield the continuity equation. Del dot j plus partial rho on partial t is equivalent to 0. Current is the movement of charge. The continuity equation says that if charge is moving out of a differential volume, like the divergence of current density is positive, then the amount of charge within that volume is going to decrease. So the rate of change of charge density is negative. Therefore, the continuity equation amounts to a conservation of charge. If magnetic monopoles exist, there will be continuity equation for monopole currents as well. In fluid dynamics, the continuity equation states that the rate at which mass enters a system is equal to the rate at which mass leaves the system, plus the accumulation of mass within the system. The differential form is as shown, where rho is fluid density, t is time, and u is the flow velocity vector field. The term derivative can be understood as the accumulation or loss of mass in the system, while the divergence term represents the difference in flow versus flow out. In this context, this equation is also one of the Euler's equations. In fluid dynamics, the Navier-Stokes equation form a vector continuity equation describing the conservation of linear momentum. If the fluid is incompressible, volumetric strain rate is 0, the mass continuity equation simplifies to volume continuity equation. Del dot u is equivalent to 0, which means that the divergence of the velocity field is 0 everywhere. Physically, this is equivalent to saying that the local volume dilation rate is 0. Hence, a flow of water through a converging pipe will adjust solely by decreasing its velocity as water is largely incompressible. In computer vision, optical flow is the pattern of apparent motion of objects in a visual scene. Under the assumption that brightness of the moving object do not change between two image frames, one can derive the optical flow equation as shown, where t is time, xy coordinates are those in the image, I is the image intensity at image coordinate xy and time t, V is the optical flow velocity vector. Vx, Vy at image coordinate xy and time t. Conservation of energy says that energy cannot be created or destroyed. Therefore, there is a continuity equation for energy flow. Partial U on partial T plus del dot Q is equivalent to 0, where U is the local energy density, energy per unit volume. Q is the energy flow, transfer of energy per unit cross-sectional area per unit time is a vector. An important practical example is the flow of heat. When heat flows inside a solid, the continuity equation can be combined with Fourier's law. Heat flux is proportional to the temperature gradient to arrive at the heat equation. The equation of heat flow may also have a source term. Although energy cannot be created or destroyed, heat can be created from other types of energy, for example, friction or joule heating. There is a quantity that moves continuously according to a stochastic random process, like the location of a single dissolved molecule with Brownian motion. Then there is a continuity equation for its probability distribution. The flux in this case is the probability per unit area per unit time that the particle passes through a surface. According to the continuity equation, the negative divergence of this flux equals the rate of change of the probability density. The continuity equation reflects the fact that the molecule is always somewhere. The integral of its probability distribution is always equal to 1. And it moves by a continuous motion, not teleporting. Quantum mechanics is another domain where there is a continuity equation related to the conservation of probability. The terms in the equation require the following definitions and are slightly less obvious than the other examples we have seen. One is that the wave function psi for a single particle in position space rather than momentum space, that is the function of position r and time t. Psi is equivalent to psi rt. The probability density function is as shown. The probability of finding the particle within V at t is denoted and defined as shown by the equations as shown. The probability current, aka probability flux, is as shown by the equation. With these definitions, the continuity equation then reads del dot j plus partial rho on partial t is equivalent to 0, which is equivalent to del dot j plus partial psi square, the quantum wave function square on partial t is equivalent to 0. Either form may be quoted. Intuitively, the above quantities indicate these represent the flow of probability. The chance of finding the particle at some point r and time t flows like a fluid, and hence the term probability current, a vector field. The particle itself does not flow deterministically in this vector field. The 3D time-dependent Schrödinger equation and its complex conjugate are respectively as shown, where u is the potential function. The partial derivative of rho with respect to t is as shown. Multiplying the Schrödinger equation by psi with asterisk, the quantum wave function with asterisk, then solving for psi with asterisk, partial psi on partial t, and similarly multiplying the complex conjugate Schrödinger equation by psi, then solving for psi, partial psi with asterisk on partial t, we get as follows, as shown. Substituting into the time derivative of, of rho, we obtain this bunch of equations. The replacement operators del square in the above result suggests that the right hand side is the divergence of J, and the reversed order of terms implies that this is the negative of J altogether. This is shown. So the continuity equation is partial rho on partial t is equivalent to negative del dot J, which is partial p on partial t plus del dot J is equivalent to 0. The integral form follows as for the general equation. The total current flow in the semiconductor consists of drift current and diffusion current of both the electrons in the conduction band and the holes in the valence band. General form for electrons in one dimension is as shown, where n is the local concentration of electrons, mu n is the electron mobility, E is the electric field across the depletion region, dn is the diffusion coefficient for electrons, Gn is the rate of generation of electrons, Rn is the rate of recombination of electrons. And similarly for holes, we have the equation where P is the local concentration of holes, mu P is the hole mobility, E is the electric field across the depletion region, dP is the diffusion coefficient for holes, Gp is the rate of generation of holes, Rp is the rate of recombination of holes. Consider the fact that the number of electrons is conserved across the volume of semiconductor material with cross-sectional area A and length dx across the x-axis. More precisely, one can say rate of change of electron density is equivalent to electron flux in minus electron flux out plus net generation inside a volume, and can be represented mathematically as shown. Here J denotes the current density, whose direction is against electron flow by convention due to the electron flow within the considered volume of the semiconductor. It is also called electron current density. Total electron current density is the sum of drift current and diffusion current densities shown. Therefore, we obtain the equation as shown. Applying the product rule results in this final expression. The key to solving these equations in real devices is, whenever possible, to select regions in which most of the mechanisms are negligible, so that the equation reduced to a much simpler form. The notation and tools for special relativity, especially for vectors and for gradients, offer a convenient way to write any continuity equation. The density of a quantity rho and its current J can be combined into a 4-factor called 4 current, where c is the speed of light. The divergence of this current is shown, where partial mu is the 4 gradient and mu is an index labeling the space-time dimension. Then the continuity equation is partial mu J mu is equivalent to 0. In the usual case where there are no sources or sinks, that is for perfectly conserved quantities like energy or charge. This continuity equation is manifestly, obviously, Lorentz invariant. Example of continuity equations often written in this form include electric charge conservation, where J is the electric for current, and energy momentum conservation, where T is a stress energy tensor. In general relativity, where space-time is curved, the continuity equation in differential form for energy, charge, and other conserved quantities involve covariant divergence instead of ordinary divergence. For example, the stress energy tensor is a second order tensor field containing energy momentum densities, energy momentum fluxes, and shear stresses over mass energy distribution. The differential form of energy momentum conservation in general relativity states that the covariant divergence of the stress energy tensor is zero. This is an important constraint on the form the Einstein field equation take in general relativity. However, the ordinary divergence of the stress energy tensor does not necessarily vanish as shown. The right hand side strictly vanishes for flat geometry only. As a consequence, the integral form of the continuity equation is difficult to define and not necessarily valid for a region within which spacetime is significantly curved, e.g. around a black hole or across the whole universe. Quarks and gluons have color change, which is always conserved like electric charge, and there is a continuity equation for such color charge currents. Explicit expression for currents are given at gluon field strength tensor. There are many other quantities in particle physics which are often or always conserved. Baryon number are proportional to the number of quarks minus the number of antiquarks. Electron number, mu number, tau number, isospin, among others. Each of these has a corresponding continuity equation, possibly including a source sink terms. One reason the conservation equations frequently occur in physics is the Noether's theorem. This states that whenever the laws of physics have a continuous symmetry, there is a continuity equation for some conserved physical quantity. The three most famous examples are 1. The laws of physics are invariant with respect to time translation. For example, the laws of physics today are the same as they were yesterday. This symmetry leads to the continuity equation for conservation of energy. 2. The laws of physics are invariant with respect to space translation. For example, the laws of physics in Kenya are the same as the laws of physics in Australia. This symmetry leads to the continuity equation for conservation of momentum. 3. The laws of physics are invariant with respect to orientation. For example, floating in outer space, there is no measurement you can do to say which way is up. The laws of physics are the same regardless of how you are oriented. This symmetry leads to the continuity equation for conservation of angular momentum. This episode is brought to you by Cisco Educational Premium. Did you know that Navier-Stokes equations are partial differential equations? In physics, the Navier-Stokes equations are partial differential equations which describe the motion of viscous fluid substances, named after French engineer and physicist Claude Louis Navier and Anglo-Irish physicist and mathematician George Gabriel Stokes. They were developed over several decades of progressively building the theories from 1822 Navier to 1842 to 1850 the Stokes. The Navier-Stokes equations mathematically express conservation of momentum and conservation of mass from Newtonian fluids. They are sometimes accompanied by an equation of state relating pressure, temperature, and density. They arise from applying Isaac Newton's second law to fluid motion, together with the assumption that the stress in the fluid is a sum of a diffusing viscous term proportional to the gradient of velocity and pressure term, hence describing viscous flow. The difference between them and closely related Euler equations is the Navier-Stokes equations take viscosity into account while Euler equations model only in viscid flow. As a result, the Navier-Stokes are a parabolic equation and therefore have better analytic properties at the expense of having less mathematical structure. For instance, they are never completely integrable. The Navier-Stokes equations are useful because they describe the physics of many phenomena of scientific and engineering interest. They may be used to model the weather, ocean currents, water flow in a pipe, and airflow around a wing. The Navier-Stokes equation in their full and simplified forms help with the design of aircraft and cars, the study of blood flow, the design of power stations, the analysis of pollution, and many other things. Coupled with Maxwell's equation, they can be used to model and study magnetohydrodynamics. The Navier-Stokes equations are also of great interest in a purely mathematical sense. Despite their wide range of practical uses, it has not yet been proven whether smooth solutions always exist in three dimensions. That is, whether they are infinitely differentiable or even just bounded at all points in the domain. This is called the Navier-Stokes existence and smoothness problem. The solution of the equations is a flow velocity. It is a vector field to every point in a fluid at any moment in a time interval. It gives a vector whose direction and magnitude are those of the velocity of the fluid at that point in space and at that moment in time. It is usually studied in three spatial dimensions and one time dimension, although two spatial dimensional and steady state cases are often used as models. And higher dimensional analogs are studied in both pure and applied mathematics. Once the velocity field is calculated, other quantities of interest such as pressure or temperature may be found using dynamical equations and relations. This is different from what one normally sees in classical mechanics where solutions are typically trajectories of position of a particle or deflection of a continuum. Studying velocity instead of position makes more sense for a fluid, although for visualization purposes, one can compute various trajectories. In particular, the streamlines of a vector field, interpreted as flow velocity, are paths along which a massless fluid particle will travel. These paths are the integral curves whose derivative at each point is equal to the vector field, and they can represent visually the behavior of the vector field at a point in time. The Navier-Stokes momentum equation can be derived as a particular form of the Cauchy momentum equation, whose general convective form is du on dt is equivalent to 1 on rho del dot sigma plus g. By setting the Cauchy stress tensor sigma to be the sum of a viscosity term tau, the deviatoric stress, and pressure term pi, volumetric stress, we arrive at the Cauchy momentum equation, at least convective form. Rho du on dt is equivalent to negative del p plus del dot tau plus rho g, where d on dt is the material derivative defined as partial on partial t plus u dot del. Rho is the density, u is the flow velocity, del dot is the divergence, p is the pressure, t is time, tau is the deviatoric stress tensor which has order 2. G represents body accelerations acting on the continuum, for example, gravity, inertial accelerations, electrostatic accelerations, and so on. In this form, it is apparent that in the assumption of an inviscid fluid, no deviatoric stress, Cauchy equations reduce to Euler equations. Assuming conservation of mass, we can use the mass continuity equation or simply continuity equation partial rho on partial t plus del dot rho u is equivalent to 0 to arrive at the conservation form of the equations of motion. This is shown Cauchy momentum equation conservation form partial on partial t rho u plus del dot rho u cross u is equivalent to negative del p plus del dot tau plus rho g as shown, where that O term with a cross is the outer product. The left side of the equation becomes acceleration and may be composed of time-dependent and convective components. Also, the effects of non-inertial coordinates if present. The right side of the equation is, in effect, a summation of hydrostatic effects, the divergence of the vectoric stress and body forces such as gravity. All non-relativistic balance equations, such as the Navier-Stokes equation, can be derived by beginning with the Cauchy equations and specifying the stress tensor through a constitutive relation. By expressing the deviatoric shear stress tensor in terms of viscosity and fluid velocity gradient and assuming constant viscosity, the Cauchy equations we have seen will lead to Navier-Stokes equations. Significant feature of the Cauchy equation and consequently all other continuum equations including Euler and Navier-Stokes is the presence of convective acceleration, the effect of acceleration of a flow with respect to space. While individual fluid particles indeed experience time-dependent acceleration, the convective acceleration of the flow field is a special effect. One example being fluid speeding up in a nozzle. It is worth pointing here that the Cauchy stress tensor is denoted sigma instead of tau as it was in general continuum equation and in incompressible flow as we have seen. The compressible momentum, just remember that, keep in mind, the compressible momentum in Navier-Stokes equation results from the assumptions on the Cauchy stress tensor. 1. The stress is a Galilean invariant. It does not depend directly on the flow velocity but only on spatial derivatives of the flow velocity. So the stress variable is the tensor gradient del u. 2. The stress tensor is linear in this variable. Sigma del u is equivalent to c del u, where c is the fourth order tensor representing the constant of proportionality called the viscosity or elasticity tensor, and thus full colon is the double dot product. 3. The fluid is assumed to be isotropic as with gases and simple liquids, and consequently V is an isotropic tensor. Furthermore, since the stress tensor is symmetric by Helmholtz decomposition, it can be expressed in terms of two scalar length parameters, the second viscosity lambda and the dynamic viscosity mu, as it is usual in linear elasticity. This episode is brought to you by Cisco Educational Premium. The incompressible momentum Navier-Stokes equation resolved from the following assumption on a Cauchy stress tensor. 1. The stress is Galilean invariant. It does not depend directly on the flow velocity but only on spatial derivatives of the flow velocity. So the stress variable is the tensor gradient del u. 2. The fluid is assumed to be isotropic as with gas and simple liquids, and consequently tau is an isotropic tensor. Furthermore, since the vectoric stress tensor can be expressed in terms of dynamic viscosity mu, Stokes stress constitutive equation expression used for incompressible elastic solids, tau is equivalent to 2 mu epsilon, where epsilon is equivalent to half del u plus del u raised to t is the rate of strain tensor. So this decomposition can be made explicit as Stokes stress constitutive equation expression used for incompressible viscous fluids, tau is equivalent to mu del u plus del u raised to t. Dynamic viscosity mu need not to be constant in compressible flows. It can depend on density and on pressure. Any equation that makes explicit one of these transport coefficient in the conservative variable is called an equation of state. The diversion of the vectoric stress is given by del dot tau is equivalent to 2 mu del dot epsilon is equivalent to mu del dot del u plus del u raised to t is equivalent to mu del square u, because del dot u is equivalent to 0 for incompressible fluid. Incompressibility rules out density and pressure waves like sound or shock waves. So this simplification is not useful if these phenomena are of interest. The incompressible flow assumption typically holds well with all fluids at low Mach numbers, say up to Mach 0.3, such as for modeling air wounds at normal temperatures. The incompressible Navier-Stokes equations are best visualized by dividing for the density as shown. If the density is constant throughout the fluid domain, or in other words, if all fluid elements have the same density, rho is equivalent to rho 0, we have as shown, where nu is equivalent to mu on rho naught is called kinematic viscosity. For example, let's look at velocity profile laminar flow. Ux is equivalent to uy is equivalent to 0, uz is equivalent to 0 for the x direction. Simplify the Navier-Stokes equation. 0 is equivalent to negative dp on dx plus mu d square u on dy square. Integrating twice to find the velocity profile with boundary condition y is equivalent to h, u is equivalent to 0, y is equivalent to negative h, u is equivalent to 0, u is equivalent to 1 on 2 mu dp on dx y square plus ay plus b. From this equation, we substitute in two boundary conditions to get two equations. 0 is equivalent to 1 on 2 mu dp on dx h square plus h plus b. 0 is equivalent to 1 on 2 mu dp on dx h square minus h plus b. Add and solve for b. B is equivalent to negative 1 on 2 mu dp on dx h square. Substitute and solve for a. A is equivalent to 0. Finally, it gives the velocity profile. U is equivalent to 1 on 2 mu dp on dx y square minus h square. It is well worth observing the meaning of each term comparing to the Cauchy momentum equation. So we have partial u on partial t plus u dot del u, all that being inertia by volume, and that part partial u on partial t being only variation. We have u dot del u being convection, and nu del square u is equivalent to negative del omega, all of that being divergence of stress, with nu del square u being only division, and negative del omega being only internal source. G is the external source. The higher order term, namely the shear stress divergence, del dot tau, are simply reduced to vector Laplacian term mu del square u. This Laplacian term can be interpreted as the difference between velocity at a point and the mean velocity in a small surrounding volume. This implies that for a Newtonian fluid, viscosity operates as a division of momentum in much the same way as the heat conduction. In fact, neglecting the conversion term incompressible Navier-Stokes equation leads to a vector division equation, namely Stokes equation. But in general, the convection term is present. So incompressible Navier-Stokes equation belong to class of convection division equations. In the usual case of an external field being a conservative field, G is equivalent to negative del phi. By defining the hydraulic head, H is equivalent to the equation as shown. H is equivalent to omega plus 5, that W thing. One can finally condense the whole source in one term, arriving to the incompressible Navier-Stokes equation with conservative external field partial u on partial t plus u dot del u minus mu del square u is equivalent to negative del h. The incompressible Navier-Stokes equations with conservative external field is the fundamental equation of hydraulics. The domain for these equations is commonly a 3 or less dimensional Euclidean space for which an orthogonal coordinate reference frame is usually set to explicit the system of scalar partial differential equations to be solved. In three-dimensional orthogonal coordinate systems are three Cartesian, cylindrical, and spherical. Expressing the Navier-Stokes vector equation in Cartesian coordinates is quite straightforward and not much influenced by the number of dimensions of the Euclidean space employed. And this is the case also for the first-order terms like the variation and convection ones. Also, in non-Cartesian orthogonal coordinate systems, but for the higher order terms, the two coming from the divergence of the deviatoric stress that distinguish Navier-Stokes equation from Euler equations. Some tensor calculus is required for reducing an expression in non-Cartesian orthogonal coordinate systems. The incompressible Navier-Stokes equation is composite sum of two orthogonal equations, as shown. This result follows from Helmholtz theorem, aka fundamental theorem of vector calculus. The first equation is pressureless, governing equation for the velocity, while the second equation for the pressure is a function of the velocity and is related to the pressure Poisson equation. The explicit functional form of the projection operator in 3D is formed from the Helmholtz theorem, shown, with a similar structure in 2D. Thus, the governing equation is an integral differential equation similar to the Coulomb and Biot-Savart law, not convenient for numerical computation. An equivalent weak or variational form of the equation proved to produce the same velocity solution as Navier-Stokes equation is given by W partial u on partial t is equivalent to negative W u dot del u minus nu del W, those full columns, del u plus W f raised to s. For divergence-free test function W satisfying appropriate boundary conditions, here the projections are accomplished by the orthogonality of the solenoidal and irrotational function spaces. The discrete form of this is eminently suited to finite element computation of divergence free flow, as we shall see in the next section. There one will be able to address the question, how does one specify pressure-driven Poiseuille problems with a pressureless governing equation? The absence of pressure forces from the governing velocity equation demonstrate that the equation is not a dynamic one, but rather a kinematic equation where the divergence-free condition serve the role of a conservation equation. This all will seem to refute the frequent statements that the incompressible pressure enforces the divergence-free condition. This episode is brought to you by Cisco Educational Premium. One property of Navier-Stokes equation is nonlinearity. The Navier-Stokes equations are nonlinear partial differential equations in the general case and so remain in almost every real situation. In some cases, such one-dimensional flow and Stokes flow or creeping flow, the equation can be simplified to linear equations. The nonlinearity makes most problems difficult or impossible to solve and is the main contributor to the turbulence that the equations model. The nonlinearity is due to convective acceleration, which is an acceleration associated with the change in velocity or position. Hence, any convective flow, whether turbulent or not, will involve nonlinearity. An example of convective but laminar non-turbulent flow will be the passage of viscous fluid, example oil, through a small converging nozzle. Such flows, whether exactly solvable or not, can often be thoroughly studied and understood. Turbulence is the time-dependent chaotic behavior seen in many fluid flows. It is generally believed that is due to the inertia of the fluid as a whole. The culmination of time-dependent and convective acceleration, hence flows where inertial effects are small, tend to be laminar. The Reynolds number quantifies how much the fluid is affected by inertia. It is believed, though not known with certainty, that if a Stokes equation describes turbulence properly, the numerical solution of the Navier-Stokes equations for turbulent flow is extremely difficult, and due to the significantly different mixing length scales that are involved in turbulent flow. The stable solution of this requires such a fine mesh resolution that the computational time becomes significantly infeasible for calculation or direct numerical simulation. Attempts to solve a turbulent flow using a laminar solver typically results in time and steady solution which fails to converge appropriately. To counter this, time average equations such as the Reynolds average Navier-Stokes equation runs, supplemented with turbulence models, are used in practical computational fluid dynamics (CFD) applications when modeling turbulent flows. Such models include the Spalart, Almaraz, K omega, K epsilon, and SST models, which add a variety of additional equations to bring closure to the Rand's equations. Large eddy simulation less can also be used to solve this equation numerically. This approach is computationally more expensive in time and in computer memory than RANDS, but produces better results because it explicitly solves the larger turbulence scales. Together with supplemental equation, for example, conservation of mass, and well-formulated boundary condition, the Navier-Stokes equation seem to model fluid motion accurately. Even turbulent flows seem, on average, to agree with real-world observations. The Navier-Stokes equation assumes that the fluid being studied is continuum. It is infinitely divisible and not composed of particles such as atoms or molecules, and is not moving at relativistic velocities. At very small scales or under extreme conditions, real fluids made out of discrete molecules will produce results different from the continuous fluids modeled by Navier-Stokes equations. For instance, capillarity of internal layers in fluids appears for flow with high gradients. For large Knudsen number of problems, the Boltzmann equation may be a suitable replacement. Failing that, one may have to resort to molecular dynamics or various hybrid methods. Another limitation is simply the complicated nature of the equations. The time-tested formulations exist for common fluid families, but the application of the Navier-Stokes equation to less common families tend to result in a very complicated formulations and often to open research problems. For this reason, these equations are usually written for Newtonian fluids where the viscosity model is linear. Truly general models for the flow of other kinds of fluids such as blood do not exist. The Navier-Stokes equations, even when written explicitly for specific fluids, are rather generic in nature, and their proper application to specific problems can be very diverse. This is partly because there is an enormous variety of problems that may be modeled, ranging from as simple as the distribution of static pressure to as complicated as the multi-phase flow driven by surface tension. Generally, the application to specific problems begin with some flow assumptions and initial stroke boundary condition formulation. This may be followed by scale analysis to further simplify the problem. Assume steady parallel one-dimensional non-convective pressure-driven flow between parallel plates. The resulting scaled dimensionless boundary problem is this square u on dy square is equivalent to -1, u0 is equivalent to u1 is equivalent to 0. The boundary condition is the no-slip condition. This problem is easily solved for the flow field uy is equivalent to y minus y square on 2. From this point onward, more quantities of interest can be easily obtained, such as the viscous drag force or net flow rate. Difficulties may arise when the problem becomes slightly more complicated. A seemingly modest twist on the parallel flow above will be the radial flow between parallel plates. This involves convection and thus nonlinearity. The velocity field may be represented by the function Fz and must satisfy the equation as shown. The ordinary differential equation is what is obtained when the Navier-Stokes equations are written and the flow assumption applied. Additionally, the pressure gradient is solved for. The nonlinear term makes this a very difficult problem to solve analytically. A lengthy implicit solution may be found, which involves elliptic integrals and roots of cubic polynomials. Issues with the actual existence of solution arise for r greater than 1.41 approximately. This is not root 2. The parameter r being the Reynolds number with appropriate chosen scales. This is an example of flow assumptions losing their applicability and an example of the difficulty in high Reynolds number flows. A type of natural convection can be described by Navier-Stokes equation is the Rayleigh-Bennett convection. It is one of the most commonly studied convection phenomena because of its analytical and experimental accessibility. This episode is brought to you by Cisco Educational Premium. Some exact solutions to the Navier-Stokes equation exist. Example of degenerate cases with the nonlinear terms in the Navier-Stokes equation equal to 0 are Poiseuille flow, Coyote flow, and the oscillatory Stokes boundary layer. But also more interesting example solution to the full nonlinear equation exists, such as Jeffrey-Hemmel flow, von Karman-Zwilling flow, stagnation point flow, Landau-Squeeze-Jet, Taylor-Green vortex. Note that the existence of this exact solution does not imply that they are stable. Turbulence may develop at higher Reynolds numbers. Under additional assumptions, the component paths can be separated. For example, in the case of an unbounded planar domain with two-dimensional incompressible and stationary flow in polar coordinates r, phi, the velocity components ur and u phi and pressure p are shown, where n and b are arbitrary constants. The solution is valid in the domain r greater than or equal to 1 and for a less than -2 nu. The Cartesian coordinates when the viscosity is 0, nu is equivalent to 0, that is, the vxy and pxy's are shown. Let us look at a three-dimensional example. In the case of an unbound Euclidean domain with three-dimensional incompressible stationary and with 0 viscosity, nu is equivalent to 0. Radial flow in Cartesian coordinates xy and z, the velocity vector v and pressure p are vxyz and pxyz as shown. There is a singularity at x is equivalent to y is equivalent to z is equivalent to 0. The steady state example with no singularities comes from considering the flow along the lines of vibration. Let R be a constant radius of the inner coil. One set of solution is given by Pxyz, rho xyz, u xyz as shown, where G is equivalent to 0 and mu is equivalent to 0 for arbitrary constant A and B. This is a solution in a non-viscous gas, incompressible fluid, whose density, velocities, and pressure goes to 0 far from the origin. No, this is not a solution to the clay millennium problem because that refers to the incompressible fluids where rho is a constant, and neither does it deal with uniqueness of Navier-Stokes. question with respect to any turbulence properties.